not ready yet.
You're not ready yet, but connect to the.
Okay.
Tu bloques ton micro, ton. Ah, cool. Ton haut-parleur aussi. Ton haut-parleur aussi. Hein?
Yes, I already did that.
Okay. I'm gonna dim the light.
Okay. Hello everyone.
Voilà.
Okay.
Merci
Can
beaucoup.
Everybody hear me?
Yes, we can hear you.
Okay, thank you. Yeah, I can hear you too as well. Thank you.
So everyone is muted, unless the president. So president, please reactivate your microphone. Thanks a lot.
So you hear me? Okay.
Yeah, yes.
So Frédéric, you're ready?
Not yet. I need to share my screen first. I need your help.
Okay. Just try. On this channel, we are only the jury on Frédéric. I mean, nobody else. Okay.
No.
Okay. There in the room we are in area. We have 3 people in the audience, right? Only.
Okay. Great.
Jean-Baptiste, I need you to allow me to share the screen.
Sorry.
Otherwise, nobody will see anything. Okay. Sorry, please give me a moment. I think that's the one. I hope.
Okay. Just try to move to the next slide.
Yes.
Okay, that's fine. Okay, so we could start.
Okay. Thank you.
Okay. Okay, so Frédéric, we'll start. You will start your defense. Okay, so you have 45 minutes. Okay, please go.
Thank you for your introduction. Thank you all for your presence today. My thesis is entitled Quantification of Wildland Fire Risk using Metamodeling of Fire Spread. I worked under the supervision of Vivien Mallet and Jean-Baptiste Filippi, and my PhD director is Jacques Sainte-Marie. This thesis is also part of the Firecaster research project by Jean-Baptiste coordinated. Most of wildland fires will end up in a burn surface of less than 1 hectare, but there are also some extreme cases that can go up to more than 10,000 hectares, such as the recent mega fires in Australia and California. The difference between these fires can be explained by the variety of the environmental conditions, the moisture of the fuel. So the fuel here for wildland fires is the vegetation, the type of vegetation, wind speed, slope, etc. And these factors will have an influence at the very local scale on the evolution of the fire front. On the animation on the right, you can see the simulation of fire spread. So the fire front here evolves across the land. It's represented by the red contour with the burnt surface inside and the rest of the land that is not burnt outside of the contour. Several decision support systems exist to manage wildland fires. Some are used for crisis situations, let's say shortly a fire has started. Some are used for short-term planning. Before a fire has started, in case it starts during the day, but planning can also be made on the long term. In the crisis situations, we have, for instance, burn probability maps that indicate the probability of a location to belong to the burn surface after some given time. This can result from an ensemble of wildland fire spread simulations. For the short term, we have fire danger maps that indicate the proneness to ignition and spread of the fire, but usually they do not rely on simulation of the fire spread. They use danger indices such as the fire weather index that are more easy to compute and usually only depend on weather information. the main goal of my thesis was to make the most use of wildland fire simulations in crisis situations and short-term situations. And a key aspect to consider is the computational time for these applications. So to address the possible issues when a high number of simulations are required, a strategy was to use a metamodel, a so-called an emulator. So by denoting my model as M, its input as X, and its output or some output of interest of the model as Y, an emulator consists in a model M tilde, which is approximately equal to M, but that is much faster to compute and that we use instead of the original model. Still, with our models, there are several challenges that need to be addressed. First is to consider the sources of uncertainty in the model. In my thesis, I focused on input uncertainty, and the challenge is to properly propagate the probability distributions of the input through the model. Also, when we have probabilistic predictions, such as burn probability maps, there's the question of how to evaluate these maps, but using deterministic and not probabilistic observations. And other challenges in metamodeling and with our models are due to the fact that we have high dimensional input data, for instance, X in a space of dimension 100,000, and also a special type of output that are the burn surfaces that I consider from a binary perspective. As for any point in the map, you will either inside the burn surface or outside of it. And so finally, during this work, I studied Corsica Island. So on the previous map, it's located here, southeast of France. That's the island here. Sorry. And the model I used to run simulations of wildland fire spread is ForFire, which is a front tracker solver relying on a macros method. And I used it together with the surface vector spread model of Overfitting. Also to run the simulations, I used data that were available thanks to the Firecaster project. So we have terrain data, elevation for Corsica, and land use on the right. At high spatial resolution of 80 meters. And I also used weather forecasts and observations of past fires. So first, in my thesis, I focused on the distribution of the input and their propagation through the model to generate a burn probability map for crisis situations. And then I calibrated the input distributions. So these are the two first sections of my presentation, and the next two focus on fire danger mapping for the short term. And by using by using wildland fire spread, I needed to build an emulator to address computational time. So I'll focus. These are the next two parts of my presentation, and I add in some conclusions and perspectives. So the first part is about the generation and evaluation of an ensemble of fire spread simulations. It led to the publication of a paper. So as I mentioned, the application is burn probability map, and I focused on past crisis situations, specifically seven relatively big fires that occurred in Corsica Island. The input X of my simulations consists in data that was available at the time of the fires. So we have, I have a presumed time and location of fire start, past weather forecasts, and I needed to use an estimated fire duration, and of course there's the terrain data to run the simulations. And for evaluation purposes, I used the final observed burn surface of a fire. And the generation of my ensemble relies on a classical Monte Carlo approach. Here, the specificity is that since the input X depends on the fire, input uncertainty here is represented thanks to a perturbation vector U with several components that are applied to the input X. And U has a probability distribution that we propagate through the model. it consists simply in drawing n realizations of perturbation vector u and running the corresponding simulations, so that for any point Si in the map, the corresponding burn probability Pi is equal to the number of simulations where Si is in the burn surface divided by the total number of simulations. But for this to work, a key aspect is to have an input probability distribution. So to get a better idea of better knowledge of the inputs involved in the simulations, I did some literature review, and with some bit of expert knowledge, I was able to provide ranges that were relevant for my perturbations parameters. So the components of U are independent, and for the most part follow normal probability distributions with truncation. So for instance, there is a perturbation on wind direction that can range from -60 degrees to +60 degrees. For fuel load, for instance, I have a multiplicative perturbation, one per fuel type. So I have several perturbations here that in each can range from -30% to +30%. So in the end, I have a perturbation vector in a space of size 48, so I applied this method by generating an ensemble of size 500 for each of the fires, and I was able to do so faster than real time, but it's required to distribute the computations on the 30 CPU machine. And here's an example of the resulting burn probability map for one of the fires, that of Calenzana. On the left, over time, and on the right, we have based on the end of each simulation of a wildland fire spread. And the black and white contour here corresponds to the final observed burn surface. And when we have that, we want to evaluate the performance of a prediction. But since we have a probabilistic prediction, using the deterministic observation is not straightforward. So to do so, I used evaluation properties and tools. I'm going to present only a few ones here that are more commonly found in meteorological applications. For instance, accuracy, which means the overall agreement between observation and prediction. So by defining for a point Si the observation variable OI, which is equal to 1 if the point is inside the burn surface, the observed one, and 0 otherwise, the Breyer score is the mean of the squared difference between observation of OI and burn probability PI. And also for accuracy, we can use I used the Breyer skill score, which is equal to 1 minus BS divided by a reference Breyer score using a constant burn probability. So with a map with the same probability everywhere in some way. When we have higher accuracy with PI instead of a constant probability based on BS, BSS is positive, otherwise it's negative, and BSS can go up to 1. Another property is consistency, which can be understood as the fact that that the observation is undistinguishable from any randomly selected member of the ensemble of a large number of observations. For that, I used the rank, but here the rank is usually defined for continuous variables where there is generally no equality. But since here I'm in a binary case with zeros and ones, I had to adapt the definition of a rank. So I defined a weight vector, and with this definition that I had to adapt, I have the same property as for continuous variables. That is to say that if an ensemble is consistent, then we obtain a flat rank histogram. So here's the fire from before. On the top right is sharpness and reliability diagram. So I'm not going to present this part, but we can see the rank histogram on the bottom right. And the ideal flat histogram is represented by the dotted line. And we can see that we are very close to the flat ideal consistent case. Sorry. And we also have good accuracy with a positive BSS for this fire. Here are a few other examples. So here we can see on the rank histogram that we have higher bars on the left and lower on the right compared to the ideal one. And this conveys the fact that we have some over prediction, too high burn probabilities. As we can see on the map, we have high burn probabilities inside the burn surface, but also outside of it. The BSS is still positive, and out of the 7 fires, there were especially 2 of them with severe overprediction, as seen on the rank histogram, but also on the burn probability map compared to the observation. With here for the Nonza case, the BSS was negative. We had poor accuracy. So that's all for this part. So given a method for generation and evaluation of probabilistic forecasts, natural next step is to calibrate the input distribution so as to increase the accuracy of a prediction, for instance. So here, since we are focusing on the output and its observed counterpart to update the input, we are in a problem of inverse uncertainty quantification. So this part led to the publication of a paper as well. And so this took me quite some time. At first, I tried several input distributions, different from the previous one. And I settled on one with uniform marginals for the components and a wider range for the most part. So this new input distribution allowed me to obtain higher accuracy. And for this part, this is my prior input distribution that whose PDF is denoted as F here. In inverse uncertainty quantification, a natural step strategy is to use as a calibrated input distribution the posterior distribution of U, whose PDF I denote as P here, which can be obtained using Bayes rule. So the posterior PDF is equal to a product of a likelihood function times the prior divided by the integral of this product. But the main problem here is the definition of the likelihood. The idea is that it should be high for a simulated burn surface. So the likelihood of S ops knowing U should be high when the corresponding simulated burn surface SU is close to the observed one. But since we have surfaces here, the traditional assumption of independent Gaussian errors is not going to work very well. We have binary variables with spatial correlations. Another problem is the untractability of a denominator, which is a high dimensional integral. So yeah, it took me quite some time to propose a suitable definition for the likelihood function in this situation of surfaces comparison. First, so I decided to propose a pseudo likelihood function, which satisfies the property that I mentioned before. It's the exponential of minus a constant coefficient beta times an energy function E. And this energy function, I want it to be equal to 0 when the two surfaces match and increase when the dissimilarity increases. The problem here is to choose the energy function. So I finally was able to reach a suitable candidate in the field of optimal transport. I used the Wasserstein distance, which can be understood here as the amount of energy that's required to move the points of one surface so that it matches the other surface. Actually, the Wasserstein distance is a distance between probability distributions. So, but the adaptation for surface comparison was relatively straightforward. So actually, my energy function, since I have 7 fires and not just one, is a weighted sum of each individual passage time distance obtained with perturbation vector u. And regarding the untractability of the denominator in this formula, since it does not depend on u due to the integral, actually we know the posterior PDF up to some multiplicative constant. So we can use the Metropolis-Hastings algorithm to generate a Markov chain representing the posterior PDF. But then I encountered another problem, that is that I need a high number of iterations with the Metropolis-Hastings algorithm. And at each time, I need to compute the energy function, so make 7 simulations, compute 7 Wasserstein distances, and do that a high number of times. And without an emulator, it would have taken too long. So the strategy I used for emulation of my energy function here was to use a Gaussian process emulator to train my Gaussian process. In terms of design of experiments, I used a training sample of size 4000 based on a Latin hypersquare sample. And but since the Gaussian process leads to no error at the points of the training sample, to evaluate the approximation error using the emulator instead of the actual function, we need a test sample to do so. Here I used one of size 2000 based on a Sobol sequence, and approximation error here was evaluated using the Q2 metric, which has a similar structure to the BSS. And when there's no error between emulator and actual function, it's equal to 1. And then it decreases when there's more error. Here I obtained Q2 of 95.3%, which is close to 1. And with the emulator, I was able to compute the 150,000 iterations of the Metropolis-Hastings algorithm in about a day. So I did that for several, I repeated this procedure for several values of beta, not the emulation, but the Metropolis-Hastings algorithm, sorry. And here are some of the results. So here we can see the marginals of the perturbation vector. In blue, we have the histogram obtained with the Metropolis-Hastings algorithm based on the Markov chain with a posterior PDF, and the black line indicates the prior PDF. One of the main results is that with a posterior, we favor perturbations that reduce rate of spread, such as an additive coefficient that's negative for combustion enthalpy, that's more likely than a positive one. That's also the case for other parameters. And regarding wind direction, we have a lower standard deviation with the posterior than using the prior. So in some sense, it reduces uncertainty on this variable after calibration. With this, so here it's for beta equal to 0.5. And so here are the results, the resulting bond probability maps with calibrated input distributions. So to the left is with input distributions from the previous section. In the middle, it's with the prior distributions with larger ranges. And to the right, it's with a calibrated distribution with beta equal to 2. And we can see that this reduction of uncertainty, we have less spread out bond probabilities compared to the prior for most cases. And this also tends to limit the overprediction problems that I had for some fires. Unfortunately, this did not lead to an increase in accuracy for all fires, only for some of them, mostly the ones where we had overprediction. So where there was not a single value of beta out of all the ones tested that came out as the best. So for the rest of my work, I decided to choose a value of beta equal to 0.5. That did not limit over prediction. That limited over prediction, but not too much. So that's it in terms of application to crisis situation and burn probability maps. This part and the next focus on fire danger mapping using simulations of wildland fire spread. And here I had to consider a much more difficult emulation problem than the one from the previous part. This part led to the publication of a paper as well. So as I mentioned, we are in short-term planning situation. The goal is to provide a high resolution fire danger map, but this time that covers the entire Corsica island. Because we do not know where a fire is going to ignite. And I wanted a high resolution map with the data I have at 80 meters. This leads to a map with about 1 million points. So an idea to use fire spread simulations to obtain a fire danger index that represents a potential fire spread was to simply simulate 1 hour fire and give as the fire danger index the corresponding fire size in hectares. But the problem is that to make the 1 million computations for fire, it would take too much time. So this is why we need an emulator here. So I wrote y equal to m of x prime. Here I made the distinction between 2 inputs. The output is relatively simple. It's our potential fire size in hectares. And there's the input x, which corresponds here to the terrain data. And here I consider it in a 20-kilometer site square that is centered around my ignition point that can be anywhere in Corsica. And I have 4 fields of terrain, 1 describing elevation and 3 describing a field parameter in my model. The other input is a vector of dimension 46, while the other one has very high dimension, I forgot to mention, but that's a key aspect. It's about 260,000, sorry. And X-prime, we have perturbations in field parameters from the previous sections. Of course, the ignition point coordinates that can be anywhere in Corsica, and wind speed and fuel moisture content that also have a very wide range. So given all these input conditions, we have an output that has a very high variance. Here are 2 examples. So in the background, we have the land cover in our square, the ignition point in the middle, and the 1 hour simulated burn surface is represented by the shaded area here. And on the left, it's 20 times larger than the one on the right. And what's challenging here for the emulator is to be able to process this high dimensional input data. The terrain is very different from one case to another. But the problem is the ability to extract which parts will contribute to fire spread or will not. Some will simply stop the spread of the fires. As in here, we have an urban area that stops the fire. And to extract these relevant features for fire spread, traditional emulation techniques such as Gaussian process modeling are not going to work, partly because we have very high dimensional data. And a very complex function to emulate. So the solution I proposed was to use a neural network. The reason behind the choice of a neural network instead of a more traditional technique is due to its ability to identify key features in images. For instance, we have convolutional neural networks that can carry out classification tasks, sorry, very efficiently. So here, my terrain data is similar to an image. I have with 4 channels in some way. So I decided to process this part with a neural network that has convolutional layers for the most part. And the vectors are processed using fully connected, also known as dense layers. So here we have a hybrid architecture so that the 2 types of inputs are processed appropriately. And there is also an important trick here to note regarding emulation. Actually, since for any fuel cell in the map, I have about 1 million of them, but each one has its own surrounding terrain. So the thing I did for emulation was to pre-compute the top part, pre-compute the vector of size 1000 here. And the emulator consists, so I did that for the 1 million possibilities, and the emulator consists in the rest of the network, which allows to save significant computational time significantly. But even though that's a strategy for emulation, we need to have good approximation error. So we need to train the very high number of parameters in the neural network. We have 57 million here, approximately. To do so, I used, in terms of design of experiment, a similar strategy as in the previous section, but with a much larger training sample size. Here I have a size of 5 million. Before I had only 4,000. Other than that, the training procedure was relatively standard. I used as a loss function the mean absolute error, which is defined here. And I used an ADA delta optimizer, which is a type of gradient, stochastic gradient descent algorithm. The implementation was done in TensorFlow, and in terms of hardware, I used the resources of the supercomputer Jean-Sainte. I used a node, a GPU accelerated node, which allowed me to carry out the 100 epochs of training in about 10 days still, even with high performance resources. So the figure on the right shows the evolution of the loss function in the test data sets with the solid line over training. And we can see that overall it decreases until it seems to stop decreasing after about 80 epochs with mean absolute error of approximately 80 hectares. So 80 hectares may seem like a lot here for a burnt surface, but given the wide variety of input conditions, actually it's a lot, an error of 80 for a given surface is a lot when it's equal, when it's about 10 hectares, but it's not that much when it's 1000. So actually, we obtained good approximation with the emulator. For instance, if I compare the emulated area for members of a test data set with the simulated counterparts, most of them are comprised between half or twice the simulated, the actual value. And in terms of metrics, we have standardized mean squared error, which is 1 minus the Q2 that I presented before. So we want it to be close to 0. And with the emulator, this value was of only 6% for the test data set. And another key result, is that with a 32 CPU machine, so not on the Jean-Sainte supercomputer, I was able to obtain a speed up factor of several thousands with the emulator compared to the wildland fire simulator, which is excellent. So the emulator, I call it deep fire in the rest of this presentation. And we can see that deep fire, before moving on, for fire danger mapping, but with no perturbations, and at each point, the same value of input wind speed and fuel moisture content. We have the map on the left. So the white locations indicate locations where ignition and spread are not possible. And with a southwestern wind, we can see that at the southwest of these unburnable locations, the potential fire size is lower, which is consistent with the physics of fire spread, because the fire will be stopped by these locations in white here. And with variation, by changing this wind speed vector, we observe the same effect, which confirms that we have good approximation error with the emulator, a good approximation. So that's it for the emulator. And now I'm going to present its application to fire danger mapping in the short term. But using actual weather forecasts this time, and not just constant values for the inputs on the map. So this led to a paper, but that's only submitted at the moment. So here I used for fire danger mapping, weather forecasts data to obtain wind speed and fuel moisture content. And we have a weather forecast with a time step of 10 minutes between each forecast step that covers 32 hours. It has 600-meter resolution. My maps are still at 80-meter resolution, so I had to carry out some interpolation. But with the temporal resolution, if I want a sequence of maps covering the whole forecasts at high resolution of 80 meter, I have 1 million times 250, so 250 million deep fire calls to run. And I was able to do so with my 32 CPU machine in only 2 hours, while it would probably have take months with for fire instead of deep fire. So the sequence, the animation in the bottom. To the left, we have the prediction with deep fire based on at each forecast time step. So we have its evolution over time, but we cannot see very well where it's lower or higher with this color scale. So here in the middle, I have a categorical representation, and these categories correspond to danger classes in a sense. For instance, we have class E, which is high danger here, and corresponds to potential burn surfaces predicted with the emulator, but are higher than 120 hectares. And also for this part, I worked with Météo France, who provides fire danger maps predictions based on the weather forecasts. And they use a fire danger index called IEP, which depends on wind speed and fuel moisture, and not the terrain data. And we can see the corresponding map on the right, which is used for comparison. So for here we have the forecast for the day of Calenzana fire. I did that for others, and overall the high danger classes, well, there is an agreement generally between IEP and deep fire due to the sensitivity of the output to the weather input in both cases. But we can see that the map in the middle is more granular in some way. We have, because it accounts for the surrounding terrain and the fact that it cannot spread sometimes because there is the sea, for instance. So here I was also able, so I built the emulator so as to account for input uncertainty. So I was able to propagate it through my DeepFire, And so here, by taking the DeepFire prediction at the location of the, at the ignition point for Calenzana fire and see its evolution over time, without perturbation, I had the black line, and the blue lines represents the evolution, but for an ensemble of size 10,000. The blue areas delineates deciles and quartiles, and in blue, solid and dotted, we have the median and mean, respectively. So it has the same variations over time as for the forecast without perturbations in black. And what we notice is that at the beginning of the day, fire danger was low, but during the afternoon, it became moderate and even high. The time of ignition here is represented by this vertical bar. And what I noticed for most of the fires is that there was high danger, or at least moderate danger, predicted by DeepFire around the time of ignition, not necessarily at the exact time, or in the vicinity of the ignition point. Oops, sorry, I wasn't finished yet. And I also noticed in most cases that the standard deviation of the output of the ensemble, sorry, is of the same order of magnitude as the mean. Another thing that I can do, so I can still propagate the uncertainty to obtain an ensemble, but if I want a sequence of maps, this takes way too much time at high spatial resolution. So I had to decrease it to 640 meters. And here I generated an ensemble size 100. And we can see at the time of ignition, the maps predicted by the ensemble, but here I only represented the quantiles at each point in my ensemble of size 100. So we have, and I think that it conveys pretty well the idea of the standard deviation, the spread of the output DeepFire distribution of the ensemble. We have the minimum that can be seen as an optimistic scenario where there's low fire danger, and the maximum is a pessimistic one. So the minimum and the maximum are maybe a bit unrealistic, but the quantiles in between can represent this distribution pretty well, from from more optimistic to more pessimistic. And finally, based on the forecasts of fire danger with high temporal resolutions, I could propose summarized daily fire danger map. So here, the quantity I propose to you, I present, is the time for each location, where it's in a high fire danger class E here. So it can range from 0 to 24 hours here. And to the left, we have it based on a single high resolution sequence of DeepFire maps, and to the right with its counterpart, but using an ensemble at lower resolution. And here, for instance, we observe that the mean of the ensemble, which is represented on the right, is more homogeneous on the map than its deterministic counterpart. So to finish, I would like to present some conclusions and perspectives for this work. So overall, I first focused on crisis situations and burn probability maps, and on the propagation of input distributions in my fire spread model, and then the calibration of this input distribution. And for fire danger mapping at high resolution in short-term planning applications, I I had to use an emulator, which ended up being based on a neural network that accounts not only for weather and uncertainty, but also for the terrain surrounding the ignition point. And this can lead to these high resolution fire danger maps of potential fire size and not weather fire danger index. I did not present today before part of my work. Actually, it's work in the Firecaster project that was led by Antoine Belgoder, and he focused, he studied the estimation of the cost of a fire. So not burn surface in hectares, but the assets it contains and what costs it corresponds to. For example, agricultural land and buildings, etc. So my contribution to this work was to provide ensembles of fire spread simulations based on my calibrated distribution obtained that I presented in the previous section. And this allowed to compute the evolution of not a mean cost over time for several fires, but of a certainty equivalent cost that accounts for risk aversion when we have very high cost associated to high damage associated to a fire. The perspectives of this PhD are to include this cost and ignition probability models to have a complete risk quantification framework, and also maybe add other sources of uncertainty and use not only observed burn surfaces, but intermediate surfaces, because we have dynamic simulations. And I conclude with, so I'm a bit short on time, sorry. We could emulate more complex scenarios with a neural network that has a time sequence as an input, or a burn surface as the output, or maybe even the fire cost as the output instead of the number of hectares based on the work of Antoine. And we could also consider optimization based on the fire danger maps, optimization problems. That's it for this presentation. Thank you for your attention.
Okay. So you hear me?
Yeah.
Oui, on vous entend très bien.
Okay, merci. Okay.
Sorry.
That's fine. So thank you, Frédéric, for the clear presentation. So we will switch to questions by the jury, and I propose that Mark starts with the question. Mark will have to leave soon, and so please, Mark, will you start?
Yes, thank you very much. I really enjoyed your presentation, and I enjoyed reading your papers, Frédéric. This work is going to take me quite a while to fully understand and see the applicability here to our situation in the United States. But I just have a few questions for you. Do you plan on comparing your fire danger maps that you've generated so easily with the emulation to actual fire occurrence, either historical records or to, in the coming years, compare it with the actual occurrence of fires or their sizes?
Yes, thank you for your comments. Yes, that's where I wasn't able to have enough time to complete it in this PhD. But one of the things we would like to do is to use the historical database. For example, in France, we have the Prométhée database, which provides fire sizes of past fires from 1973 until today. And what could be interesting is to compare the distribution based on a high number of the fire predictions with these observed fire sizes. But what's complicated here is that these fires depend on firefighting actions that are not modeled. Here I only use simulations with free spread, and it's with deep fire, it's not necessarily 1 hour. It's always 1 hour fire, while actually we have firefighting actions that occur, and the fire can be much shorter or much longer. So that's a difficulty that needs to be addressed, and that wasn't really obvious. So I haven't done much on that, unfortunately.
Yeah, thanks. You're right. I mean, it's a lot more complicated than just comparing observed fire occurrence or fire growth. But still, I think the data that you're generating with this emulation are readily compared and would show people, you know, the utility of these maps and this kind of fire danger rating approach, you know, for practical use.
Yes.
Yeah, one more question. So you the utility of your emulation approach seems to be that it's very efficient in generating these spatial surfaces of potential fire growth or other characteristics for short-term simulations. I'm curious about your thoughts on how, or would it be possible, I guess, and if so, how could you use this to generate, you know, long-term, not just 1 hour predictions, but say predictions of fire growth or emulations of fire growth or fire probability over days, for example, because the computational burden of just doing that with the simulation is very high. So if you had your emulation method, you know, could it be adapted for longer term simulations?
So on the principle, it could be adapted, yes, but here I was able to constitute a very large database, but it still took quite a lot of time to obtain my 5 million simulations. So the problem here is that the longer the fire, the more computational time, because the simulated fire size will become much higher. So there are more computations involved. So a difficulty would be to generate a high enough number of a large enough training database, but that could take quite a lot of time, unfortunately. So for long fires, in any case.
Yeah.
Sorry, that was all.
No, I agree with you. At some point, maybe when we see each other at a meeting, maybe we could talk about this problem, because I have a lot of data generated by simulation that maybe would be suitable to try your technique out. But anyway, thank you. There's a lot of value in the work that you've done here. One last quick question here. So you applied your deep learning method to what are pretty complex fire growth problems, fire behavior problems, dealing with 2 dimensions and, you know, time varying weather. I'm just wondering whether what your thoughts are on applying this to something fairly straightforward, and that would be just capturing the fire behavior response of, say, the Rothermel spread equation or any of the fire behavior models, right? So that you wouldn't have to actually simulate them, and this would probably not be much of a benefit for the current current fire behavior spread rate predictions, because they're fairly fast. But say someday, if we have a high fidelity physical model of fire behavior that takes too long, could we use an emulation procedure like what you've got here to simply predict this fire spread and fire intensity responses over the full range of environmental conditions?
Yes, for more complex models, yeah, as you mentioned, for rate of spread models, since they are much faster to compute, actually they are involved in the fire growth simulations, but we need to compute them several times. Using an emulator doesn't make much sense. it would make much more sense for a model that has high computational time. But the problem here depends on the, well, there's also the problem of the dimension of the input that would need to be addressed, because for physical models, I think that they would maybe account for weather atmospheric variables, maybe, for instance, and it's not straightforward to emulate them, maybe with a neural network, but I don't know. And there's also still the problem of with such complex models, maybe we would need a large training database to carry out emulation and obtain low approximation error. So these would be two difficulties, but it would be still very relevant to use an emulator for such for models with such high computational time.
Yeah. All right. Thank you very much.
Thank you too.
Okay. Thank you, Mark. Thanks a lot. And so we'll move now to the rewards, sorry, of this work. And maybe we could start with Jan. Jan, please.
I actually had a similar question as Mark, because I think it would be very interesting to derive a model by machine learning from the raw data rather than outputs of simulations. Could you comment on that? Are you going in that direction?
I'm sorry, of raw data and output of simulations? I'm
no,
sure.
Instead of output of simulations.
Instead of, sorry, I didn't catch
yeah.
that.
So how would you, if you were to do that, how would you retrieve the rate of spread from images, for example?
Yeah, I just like that. I have no clear idea, so I'm still thinking while answering. But I know there are some approaches that rely on raw data in wildland fire science, using machine learning and maybe neural networks for instance, fire detection. Oops, sorry.
Yeah, I really liked your use of the convolutional neural networks.
I think that the convolutional
yeah, for spatial data, I think that was very appropriate.
But if we want, for instance, sequences, well, there are recurrent neural networks. But if we have a sequence of spatial data, I'm not really sure about how to handle that. Maybe we would need to carry out some dimension reduction techniques, such as principal component analysis. Yeah, but just a few ideas. Actually, I don't haven't considered the question very much until now.
Yeah, to create a reduced model for rate of spread is, of course, in itself very interesting. Yeah. That's actually all I wanted to ask.
Oh, sorry, I'm not sure I understood. It's okay. Oh, okay, I was.
Well, I commented on the usefulness of surrogate reduced model for the rate of spread that you have been doing, and use it for probabilistic forecast. That's fast. That's a great thing.
Oh, thank you.
Okay, thank you. Thank you. Anthony, do you have some question? Well, I guess you have.
Okay, thank you.
Actually, but I have one request. Could we stop sharing screen and see each other?
Actually, I was thinking that maybe I would use parts of the presentation in appendix to answer some questions.
Okay.
But I can restart. Actually, I should maybe stop and restart again if necessary. Yeah, that's right. That's better. Thank you.
Thank you all for your time. I really enjoyed the presentation. Sorry, I have to leave. But good luck, Frédéric, and everyone. We will see you later, hopefully. Bye-bye.
Thank you, Mark. Thank you.
Bye.
Okay, so
Okay.
my turn. Yes, so Frédéric, so I wanted to start by saying that I really appreciated your manuscript. It was very well written, and your presentation was also very clear. I have a few questions. My questions will focus mainly on emulation strategies. So you considered essentially two families of approximation tools, Gaussian processes, based on a particular type of kernel and neural network. So first I would like to have a few feedback on kernel methods that you used. It seems to me that you choose the particular kernel, a matern, with a particular parameter. What is your experience on this choice, and why didn't you consider model selection strategies to choose a good kernel? Why is this one? Why is this matern 5.5? And why not more advanced techniques that are available on the shelves today to select appropriate kernels?
Yeah, actually, so first, sorry, thank you for your comments. To answer your question, I tried several methods, several kernels. So I think I tried matern 3.5, maybe a Gaussian kernel as well. And so I tried a few methods, and the best value of Q2 that I obtained was with this one, with a matern 5.5, and also a linear trend. I forgot to mention it in my presentation.
Okay.
I didn't, since I obtained good satisfactory results, I didn't really try to go beyond that.
Okay. But there are also libraries available that select the matern parameter, for example, for you, based on some maybe cross-validation techniques or other statistical estimation of the errors. You didn't consider these advanced libraries. I don't know what you used, but okay. You did it by yourself. You tested and selected the best based on the test errors.
And that's pretty much it.
Okay.
But maybe
so by the way, I have a general question on your strategy to select models. It's about so you say you do essentially estimation of the error on the test sample, and about your generation of samples. It seems to me that at some point you said, I want to have some exploration, some good exploration, so I use a LHS. Plus I had a sample to the LHS based on Sobol sequences, maybe, or I don't. Okay, at some point I did not understand clearly how you generate samples. And my question is, with this generation of samples you use, what about the statistical estimator you use to estimate errors? Because if you mix samples as you did from different distributions, then it's not so straightforward to provide a good statistical estimation of the error. So, okay, my question is, what is the relevance in statistical terms of this sample that you use that gathers, if I understood well, several samples from different distributions? So maybe you could come back on what is your training sample? Are you generated?
Yes. So my training sample is simply based on an LHS. The small one for the first simulation problem, I used I optimized it based on a discrepancy criterion with simulated annealing, algorithm available in the. I used the codes, the error codes that were available for this. So I tried to decrease the discrepancy of the LHS with
Okay.
this algorithm. But I couldn't do it for in the second problem that's still an LHS, based on an LHS, because I had a very high sample size. So with 5 million,
Okay.
the algorithm would have taken too long. So that's for the training. And yeah, the idea is to cover the input space as much as possible, based on in the first case, discrepancy criterion.
Mhm. And for the test sample.
So for the test, I generated a Sobol sequence, but for instance, I said that I had the test sample of size 2000 for the first problem. Actually, my original Sobol sequence had more points. I don't remember exactly how many. And the procedure that I used to generate the test dataset was to select points, and for each point, I compute the discrepancy of the resulting sample of having trained plus once this added point. And I did that for several points, so that at each step, I added the point that led to the smallest discrepancy based on my sequence.
Okay, then okay, I see. So it's not classical at all, I would say. It's not natural generation from the distribution, from the initial distribution. So I repeat my question. So the test errors that you compute, it seems that it is a simple average of the loss over the test sample.
That's right.
But with the sample you use, it doesn't have any statistical interpretation or straightforward statistical interpretation. What is the convergence of this test error that you converge?
Yeah, actually, I'm not really sure of how to provide a statistical estimation for this error, because if I had a different LHS, because it's
and because you keep only points satisfying some criterion. Okay, so it was not clear to me what you estimate precisely. That's the point. You can I take an average over the test sample of my loss, but if the sample is not generated according to the initial distribution, I don't know what really you estimate. Okay, so based on this saying that something is better than something else, I was not sure what is a criterion to select a model compared to another, because you don't know really what you estimate. You see my point?
Yes, I understand.
Okay.
I'm not sure if I can really answer properly, but I noticed still in terms of input distribution based on my training and test sample. For instance, the statistics of the output, but also of the marginals of the input were similar. So I guess that both samples represent the input space. I'm sorry.
Okay. Yeah, but again, if you say statistics, but if what you have generated as samples is not according to the natural distributions, I don't know exactly what you compute. You can call them statistics, but you see, if I take a Sobol sequence and I apply a classical formula for the estimation of a particular statistical moment, it's not the classical statistical estimator that you obtain. Okay, it depends on what you use for the sample. Okay, but maybe we could further discuss this question later. Well, about the neural networks, I would like to you to give me some feedback about the choice of the impact of the choice of architecture. It seems that probably you have worked a lot. You arrived with some particular topology of a network, and you show very impressive results. But I guess you experimented a lot to arrive to this. And what is the impact of the architecture, of depth, and so on? Could you give me some feedback?
Yes, there would be a lot of feedback to give, actually, because I tried several things. So I'm going to share screen again to try and explain this part, but not take too much time. So the first thing I did, well, at the very beginning of my PhD, I had never used neural networks. So oh, that's the slide. So first, I tried to carry out emulation of fire size, but on much more simple problems by using a neural network. So the first problem was by having a homogeneous terrain. So I did not use the terrain data because it's the same value everywhere, but having the scalar inputs varying. And so here I used a relatively simple neural network with 5 dense blocks. And I don't remember exactly the number of nodes. I didn't save the one, unfortunately. But when I trained it on a database of 10,000 and evaluated the SMSE on the test database of 2,000, well, I obtained the SMSE lower than 1%. So, and I had a much smaller training database, but that was only to account for the scalar part. And for the other thing I did was to fix the scalar input. And so the only thing that changed was the location of the ignition point in Corsica Island. And so for this part, I tried many architectures. So I tried, for instance, neural network, but I flattened the image data and used dense blocks. But this worked not as well as by using convolutional neural networks. And for the convolutional part, so I tried several things with stride, padding, maybe less kernels. I do not remember everything that I tried out, but I did try to change the number of block layers or the amount of layers and the number of parameters in dense or convolutional layers, or maybe using max pooling instead of average pooling.
Okay.
In the end, the best value, the best approximation for this simplified case, still with a large training sample of 100,000, was obtained with a very similar architecture to the one I presented today. So in the end, overall, there was a lot of trial and error, also in terms of loss function. And
do you think this type of architecture is quite robust in this setting, at least, in the sense that if I change a little bit the data, or maybe consider another location than Corsica and so on, do you think that you arrive to something that can be transposed to another context? Or do we need a PhD again if we change the country? Or
well, if we have the same type of input data, we could try to run to apply deep fire, of course, but I wouldn't be so sure about the approximation error because in the end, the neural network was trained for surrounding terrain for ignition points in Corsica. So maybe that could be more diverse, maybe with some few types that are more represented if we use it elsewhere. And also there's the altitude that will be different. So I don't know how well the resulting approximation will be, but we can make the computations but maybe we should train the neural network a bit more on these new territories.
Okay. From time to time, you're talking about overfitting. I rephrase you. I cite you here. You say neural networks are known to give overfitting, and in the conclusion also you come again. You talk again about this overfitting. So my question is it bad to have overfitting? I don't know if you know the recent literature on the benefit of having over parameterization and many parameters compared to the number of samples. There is an implicit regularization which come from the algorithm you use. I guess you use gradient or stochastic gradient algorithms. Yeah, only. But you use traditional descent algorithm to train your network.
Yeah, it's actually a bit more. It's a stochastic gradient descent, but with the Ada delta optimizer. Based on,
yeah. Okay. So, but the thing that I think we understand a little bit better now from simpler examples, simpler settings, that having much more parameters than the number of samples could be beneficial. If you use stochastic gradient, your algorithm will select among all solutions that are overfitting, as you say, the ones that are that have a low complexity. So, okay, there is something hidden, some regularization hidden. And then I wanted to ask you, because I saw in one application, you said, okay, I have many parameters to estimate, so I will use a much larger training sample. When you had a lot of parameters to estimate, you used a lot of samples. But did you experiment to run your gradient algorithms on a very large network with a few samples? And was it really bad, or did you really need to enrich as you did your training sample?
Yes. So to answer this question, so here I had just to clarify things. So I had about 10 times more parameters to train in my network than I had members in my training sample.
Okay.
So we are in a situation of overfitting. I did not try to train with more larger training sample size, but I did try with lower training sample size.
Okay.
Actually, generally what I noticed in all my experiments was that increasing training sample size by generating my design of experiments in the same fashion at each time, it always led to a decrease in approximation error. So here,
okay.
I have with 100,000, so that's still a lot, but that's much lower than the 5 million. And here we can see the evolution based of the error. So, and we can see that it decreases with the size of the training sample.
Yeah, okay.
So, and I think that's generally quite common for neural networks. I'm not sure about any applications, but all the applications, but for the one I did, I noticed that the higher the training sample size, the better the approximation error. And we had some trend of here it's in logarithmic scale for a few error metrics, and we have something of a trend that the error is of the order of 1 divided by n at power alpha, with alpha between 0.2 up to 0.4 for this metric, at least by trying to fit with only 3 points, but still we had a decent, pretty good fit, even though I just there are 3 training sample sizes.
Okay. I have last questions on inverse problems. So it was a nice idea. The proposal you did was for your pseudo likelihood was quite relevant. To my opinion, but I had a question: how did you arrive to this metrics that you used? You use a Wasserstein 2 metric. You could imagine other classical metrics for comparing your sets. So why did you arrive to this choice? Did you experimented other metrics?
Yes, I didn't experiment over metrics, but I guess I could have actually, because the Wasserstein distance in the end is here used as a metric between to compare 2 surfaces, and there are already existing metrics to do so. For example, there's the Sorensen, or also called dice coefficient, which is based on the area of the intersection compared to the sum of the areas of the 2 surfaces, if I remember correctly. So it's between 0 and 1. It's equal to 0 when there are no intersection, and equal to 1 when the 2 surfaces are the same. But to have something of a form between 0 and plus infinity, an energy function like that, I would have had to adapt my pseudo likelihood a little. What I liked about the Wasserstein distance is that even if I took 2 surfaces that are very far from each other, but that won't happen for our simulation because they have the ignition point in common. So they will intersect at least a little. But if I increase the distance between the surfaces, well, the Wasserstein distance will increase as well, and even more when they are even further from each other. So that felt like a more suitable metric, but I guess I could have adapted my pseudo likelihood function based on more simple scores. What I wanted to find was maybe some theoretical basis for the Wasserstein distance, in the sense that maybe by some probabilistic assumption between the error between observed one surface and simulated one, I could say the Wasserstein distance is well, we have this likelihood, and it involves the Wasserstein distance. But unfortunately, I wasn't able to find any reference or actually any leads on that. And so, yeah, I was more looking for this, and I ended up with a Wasserstein distance. I guess in the end, I could have used other approaches.
Mm-hmm. Okay. And I finished with just a comment on, so you have some probability distributions that come from the literature. You showed us a table, but afterwards, when you simulate, I think it's in chapter 2, when you perform forward UQ computation, you have a rejection, if I understood well. You impose a time limit for the computation. So when you generate a sample and the simulation is above 30 minutes, you don't consider the sample.
Yes.
I'm right? Okay. But then you have changed the distribution. You work with a conditional distribution that completely forget. It's a part of rare events, I would say, but maybe they are relevant events and important for what you are interested in.
Yeah, you
so
are right. Sorry. I'm sorry.
Yeah, so I'm done. My question is, okay, what do you do with this? What would you say?
Yes, sorry for the interruption. Yes, I just wanted to say that you're right. That's in the end, since I'm removing some of part of my sample, actually the resulting burn probability map doesn't correspond to the same input distribution. So I didn't apply this time limit for the inverse uncertainty quantification, and for the resulting burn probability maps for the prior and the posterior, it's always with the whole sample. The rejection based on this 30 minutes computational time for some simulations, which occurred for one of the fires, where actually it's a very long fire. The fire duration I used was 30 hours, which is a lot for us, at least in Corsica. The reason behind that is that in an operational context, if we want to provide a burn probability map, but the simulation are still running, and we don't have the computer is still trying to finish that, then we don't have a burn probability map in time. So so that was more practical.
Yeah. I think you are honest. Okay, when you say what you did, we limit the time and so on. You are honest, but I think it's not a good message for this type of analysis, because if you do this, it's quite dangerous, because you are manipulating another distribution, and the probability map that you give, it's not the push forward map of the input distribution you had in mind. It's something else. Okay, so what you estimate at the end, it's not really what you wanted. And okay, so I say, or you have to justify it in some sense. Maybe what you do, the rejection you do here has no impact really on the quantity of interest that you estimate at the end, but it needs to be justified and validated in some way. Looking the robustness with respect to the time of rejection, or I don't know, making some robustness or sensitivity analysis to justify this rejection. I understand that it is important from the practical point of view, but for the prediction to make sense, it has to be justified.
Yes.
And that's all for me. I leave the floor to the president. Thank you.
Thank you, Anthony. So we'll move to the next member of the jury. So I'll give the floor to Russell. Okay.
Thank you, Patrick, and thank you, Frédéric, for your presentation. You have done a really nice work and really interesting. I have a few questions. I will start from I was just wondering, when you are talking about, for example, here, the training and the testing, the accuracy of the training and the testing, the error for the cross-validation. First of all, I was wondering, do you mean like training, validation, and testing? So the question is, testing is something that the network has seen before, or is completely novel to the network?
It's completely, sorry, I didn't understand.
So when you separate your data set in training and testing,
yes,
do you have also the validation part, like training and validation or setup of your network, and then testing on data that you didn't see at all, or in some way the training data have been considered by the network before?
About the training and test data set, as I call them, the training data set is not separated in training and validation. I have only the test data set, and that's not used during training at all. But I decided to stop the training based on the evolution of error in the test data set. I'm not sure if that answers the question.
Okay, okay. So how did you train this with Python libraries or?
Yes, it's Python, TensorFlow, and Keras.
Okay.
More specifically.
Okay, I see. I was also wondering, you have said that you, of course, you are using convolutional neural network for the compression of the data. And then you use a feed-forward neural network. But did you try also some other kind of neural network, like the recurrent one, for the dynamic of the data?
No, for recurrent ones, I did not use because there was no temporal data in my emulation problem. I have a single wind speed during 1 hour. It's constant in the simulation, for instance, which explains why.
Okay.
It's in the scalar vector in my network. The terrain, well, of course, the terrain does not change over time. I mean, the altitude will not change.
No, of course not.
Time effect.
But what about the fire front?
The fire front? Yes, so I decided to focus on the final burn surface. Actually, it's the fire size, so scalar in hectares. I guess I could have considered a more complex output for my simulations and my network. So maybe as an output, we could have had a sequence of fire size, for example, every 10 minutes. I did not try to do it because I thought it was already quite complicated enough to emulate just one, but I guess we could do it. I'm not sure, I don't know recurrent neural networks well enough. I was thinking about more of a structure that, for instance, the burn surface after 10 minutes, you use it to compute the next one. So you have a bit more layers, and you have a positive output from these layers. So which would ensure that the one after 20 minutes be higher than the previous one. Maybe an architecture like that. I don't know how well it ties with recurrent neural networks.
Okay, and now still talking about, you said, for example, the wind speed is constant, etc. I have seen in your model a lot of features, which is good because you are linking with the weather, etc. But did you have an idea about which are the most meaningful features for your network?
The features, the input features?
Yes.
Yes, so actually based on the knowledge of the rate of spread model of thermal and of the physics of fire spread, the observations, what seemed pretty clear was that, so I'm going to share the screen because I have something prepared for that. The most influential input will definitely be, given the ranges I considered, fuel moisture content, wind speed, not only its norm, but also its direction. But there is the interaction with the terrain. So yeah, the location of the ignition point is also a very influential factor, because at some locations, spread will be stopped, and at others, it will be allowed to grow up to large sizes. Regarding the emulator, to check whether this sensitivity, these relevant features, input features, were accounted for properly by the emulator, I used a method called SHAP. So actually, I didn't use I used one of the algorithms of the SHAP library based on gradients, but because we have the gradients of the neural network of the emulator. And these shape values, well, in some sense, they give so here I computed them for the members of the test data set. So, and for each of these 10,000 members, each input has a given shape value. That's negative. It's if it's negative, it can assess that it tends to decrease the output file size. If it's positive, it says that this input contributes to increase the file size for this specific member. And so by using the mean absolute shape values for each input, so for position, I had to use the sum of the 1024 input vector. That's if I can find it. If it's stuck here, I should have not used that. Yes, so for position, I use the sum of the shape values for all these 1000 inputs. Sorry for the delay.
Okay.
And I obtained the following figure. So there's not here. I have a little. I have to explain which correspond to what. So the first one is fuel moisture content. The second two ones, the next are the coordinates of the risk-spin vector, and then we have the position input obtained from the sum. And then we have the perturbation of fuel parameters. And based on the way I made this perturbation for combustion enthalpy and particle density of fuel, well, I apply the same perturbation to each fuel type, while there are other perturbations that are only applied to one fuel type. So that's that explains why these two. I mean, from my perspective, that's logical to have them to be considered more influential than the other perturbations.
Yeah, of course. But so, if you go to your structure, the structure of your network, the one that you were showing right now.
I should, yeah, sorry.
Yeah, okay.
I think that's the one here. Yes.
Yeah. So if we, just to link with the comment the others have done early, Mark and Jan. So if you, especially because of the way you are like selecting the features, so the way you are underlining which are the main important features. What if in this network, instead of giving a 2D slides, a 2D image from an emulator, I give a 2D image from a satellite?
Yes.
Does the network matter?
Yes, I think we could have a network that processes such data, but I'm not sure in terms of emulation, but maybe I'm missing something here. How it would help, because here I'm only focusing on simulations of.
Yeah, sorry, I wanted to say simulations, I did simulation. But if you have, instead of having your simulations data, simulated data, historical or whatever, you use, because the way you are using them here are like a sort of 2D images, right?
Yes.
Yes. So instead of using that, you use a 2D image from a satellite. A sequence of 2D images from satellites, so not just one.
I see. I get it now. Yes, I think I could. Yeah, get the image data of the satellite that corresponds. I think that the emulation will be better using the my fields of elevation and fields of fuel parameters for the reason that these are the values that are involved in the computations of rate of spread in the simulations. For instance, the slope is computed based on at a given location based on a bilinear an interpolation. So it's really a bilinear interpolation. Yes. So it uses the closest for points from my point. So and even if in practice the elevation data could have higher spatial resolution than for my emulation problem, but the simulator doesn't know that, doesn't see that. So I don't think it would help for emulation.
Okay, I see.
I think, but maybe we could think of neural network simulator that uses satellite data. But the question would be how to train. And maybe I could use my simulations to do so. That seems a bit weird saying that, but maybe that's a possibility. I don't know.
Okay, I have only a last question about your the speed up, the execution time. I was just wondering if when you compare, you are considering both training time and testing time, and also if you are considering the same machine, the same hardware.
Yes. So here I'm considering a 32 CPU machine. So to say that I had a speed-up factor of several thousands, actually to run the simulations, actually I used several machines, but I use this best on the, so I need to remember.
It's okay.
Yes, so for each machine to constitute my training sample, the average computational time, there was a lot of simulation for each, so I had to do a bit of distribution. But if I distribute the simulation on a 32 CPU machine, based on the fact that my average simulation takes, I think in this case, it was 25 seconds for this problem. I say, well, if I were to run that many simulations, then I would have that much computational time by distributing the simulation on the 32 CPU machine.
Okay.
And for running a lot of simulations with the emulator based on this 32 CPU machine, well, I computed for a high number of simulations because actually the speed factor will, if I only have one simulation, I don't think I will obtain that good of a speed factor with TensorFlow, with a neural network. Actually, I think that we obtain much more significant speed factor by using a batch of input. So here it's based on its speed factor for running a high number of simulations. I like to point that out. I'm not sure if that answers the question.
Yeah, but it's okay, I understood. Okay, so thank you very much again. And yeah, I've done with my questions.
Thank you. Thank you, Russell. Okay, so now we will move to supervisors. Who wants to start? Jean-Baptiste, you want to start?
Oh, yes. Okay.
If you're ready.
Thanks a lot. No, I'm going to be very quick. I've got a lot of questions. Frédéric, as we wrote so many papers, and everything is already reviewed, by the way, so it's all right. And no, I've been very, very honored to work with you, Frédéric, and I hope we carry on a little bit to leave a legacy to your work. So thanks a lot, and thanks for doing. Voilà.
Thank you too.
Okay. Thank you, Jean-Baptiste. Vivien?
Yeah, so first, I'd like to say that it's been a real pleasure to work with Frédéric, but also with Jean-Baptiste for so many years. So I wanted to salute him, you know, in this final phase. And I promised for many years to Jean-Baptiste that if we could find a talented PhD student, we could do much more that we were already doing. We were doing good, I think.
You're right. Yes, very much.
Yeah, could have been doing better. And actually, that's what I think we've seen today. Because indeed, we found this talented PhD student with many skills and talents. So I wanted to point out that Frédéric, and I think you probably have seen it, he has a complete understanding of the physics, of the mathematics, and also the technological aspects, because it's not so easy. I mean, on the technical side, you have to deal with large data sets. You have to rather complex computer code. You have to make, run all the simulations distributed on a cluster. And then also he worked on a supercomputer to make this tricky training of the neural network. So, well, there was quite there were quite some technical talents involved. And on the science side, I think we can see also from the journals that there is some variety. There are publications in journals from different communities, and it's not so easy to do that in one PhD of 3 years, I have to say, because in some other countries sometimes 4 years. Here it's a 3-year PhD only, and it takes quite some dedication to do all these things and to get to the bottom of the topics with a deep understanding, as Frédéric has done. And there were no issue for us as advisor. Was easy. He could follow what we were saying very, very quickly, and he came within his own ideas, so that's very noticeable, and with a lot of rigor, and well, sometimes even too much, detail oriented. That's maybe could have done a bit more in terms of maybe statistical calibrations, as Marc mentioned in the end. But for sure, the results are very solid, and Frédéric's more likely to find bugs in your own code if you provide him with codes than to write errors himself. So. So it was an excellent PhD student. So I wanted to salute all the work and the dedication of Frédéric. Was a real pleasure to work with him, and especially that we didn't have too much work on the papers. The first draft was already nearly a paper that could be published. So that's very interesting to focus more on the science and on the things, thanks to also his writing skills. So I want finally to stress the excellent scope of the work. Starting from real life problems. At the beginning of PhD, we talked with fire workers to understand what their needs. Getting to the science, and at the bottom of the science in many respects, and then coming with real solutions that can be implemented, and that could be of use, for example, at Meteofront. So that's, I think, was very interesting to follow and supervise this work. And so thank you very much. Congratulations, Frédéric.
Thanks a lot, Vivien. Jacques, would you have some words?
Yes, thank you, Patrick. Well, Frédéric, I really want to congratulate you. I am really impressed by the work you have done, by the result you have obtained, by the publication you have submitted or that have been accepted. Really, I'm really impressed. So I really want to congratulate you. I also want to warmly thank Jean-Baptiste Filippi and Vivien Mallet for the work that I've done with you, for the supervision of your thesis. I have told you I was only the legal supervisor, but I have really no contribution for all this amount of work you have done. So once again, it was really a pleasure to exchange with you, to discuss with you. Yes, it's really a very, very good work. And as mentioned by Vivien, with a lot of aspects of applied maths. So very significant contribution over several aspects, really from the theoretical or I say upwind works till things very, very close to application. So once again, thank you for all, and it's very, very good work. And finally, I just want to say that, well, all this work has been obtained is very, I would say, deteriorated situation due to the sanitary crisis. In all the country represented by the member of the jury here, we have suffered from restriction, and it has been very, very difficult for students, for PhD students like you, like the other that are in this room, and I'm sure for the other PhD students of the member of the committee. So in this very difficult situation, it's very great performance to have obtained all these reasons. So once again, thank you and congratulations.
Thank you.
Thank you, Jacques. Thank you. Okay, so we will finish with some questions. Maybe I'll go back to a question of Anthony about Wasserstein. On how you came here. Okay, so it came naturally. I mean, it emerged naturally when you consider different distances. Did it emerge naturally when you considered when you looked for different distances between your surfaces?
Naturally, no. First, I did some research on surface comparison, and most scores I found were not involving the Wasserstein distance. So it took me quite some time. Actually, I received advice, notably from Vivien, to look in the field of optimal transport.
Okay.
That's when I ended up at the Wasserstein distance.
Okay. And you mentioned that the adaptation to the deterministic mapping was trivial, or is it? Or?
Not trivial, I'd say, but I think that I proposed a pretty natural, that's in natural from my perspective, because maybe I should go back to my slides. That's not the right part. Yes, it's here. So here, the probability, I need to, as I mentioned in this presentation, it's a distance between probability distributions. So I had to provide a probability distribution for a surface. And what came as natural to me was to use a constant PDF defined in R2. So for a point in space, the PDF is equal to a constant inside the surface and equal to 0 outside of it. And the integral over the surface leads to 1, so that we have a PDF. And so that's what I chose. I didn't really think that there was any reason to have a higher probability density elsewhere inside the surface.
Okay, so you really compare the surfaces, not the probability at a given point inside the surface. Okay. Okay. Well, maybe I have some questions about deep fire emulator. So you train it on a local surface, 20 by 20 kilometers. That's it. When you train, you consider local surface of 20 by 20. Is that right?
Yes, for the image input, yes.
Yes.
Because for most of my simulations, the simulated burn surface is going to be contained in this square. Actually, simulation domain is larger. For Corsica, we have not a simulation domain covering the whole island, but several tiles that I think are about 40 times 50 kilometers, something like that. So I only restrained to a smaller area around the burn surface, around the ignition point, sorry, because most of the time the simulated burn surface is contained inside.
Okay, okay. So does it mean that the model and the emulator will work on this specific area with specific characteristics? I mean,
yes, it's designed. It's trained.
Weather characteristics, height, altitude. I don't know, something. I mean, the question is it how much is it conditioned on the specificities? I mean, could you use a model on other characteristics on at other locations, for example, or in different conditions, different meteorological conditions?
Well, if I had different models that, for instance, included other fuel parameters or other input variables for the terrain, well, then Deepfire would not work. I guess we would have to train another similar but yet different neural network. And I think, but I'm not sure if I understood properly. I think this ties with what Anthony asked about other locations. Well, since I trained for Corsica Island, the surrounding terrain are the possible surrounding terrains in Corsica Island. So maybe in other areas that does not, there's maybe no comparable surrounding terrain. So maybe the emulator would not work as well.
Okay. Okay, but you did not consider conditioning on the specificities of the terrain, for example, or
conditioning
on the specificities of the on the local specificities. I mean,
well,
no, but
once.
Okay. If you wanted to have a model that works at other places, okay, you probably would have done differently.
Yes, I think I would have. Well,
but you did not consider that. Okay.
No.
Okay. And then you mentioned extensions to for the application. You mentioned applications to the file mapping. You mentioned extensions to time sequences. So you did not start to experiment with that? Did you?
No, I have not tried at the moment.
Okay. Okay.
Like the emulator to fire dungeon mapping, and that for my thesis at least.
Yeah. Okay. And if you consider this kind of just imagine you want to extend your work to time sequences. I mean, would you? Is the resolution, the spatial resolution, a problem? Would you like to simulate a different resolutions or not? Is it useful or not?
I'm not sure for time sequences in regards to spatial resolution. The difficulty that I would have with spatial resolution with time sequences, first I would need to rerun the simulations, and then I need to constitute my training database properly because there is going to be temporal correlations in my time sequence. So it would be more complicated to account for that. Maybe I would need to adapt my method. That's it.
Okay. And then maybe your last question about, so you showed maps, uncertainty maps, but they were big, for the application to file on mapping, you have shown uncertainty maps.
Yes.
Okay. And they were built using ensembles, right?
That's right.
Okay. And so it requires, well, let's say using a lot of computation. But did you try to, okay, did you have in mind other possibilities to model the uncertainty at the output? I mean,
well, the first thing that I wanted to do is, based on the work I did for uncertainty quantification, to propagate once again my uncertainty. So I decided to do that in the same way as before. It's a Monte Carlo approach. Actually, I should close that. Sorry. I'm sorry, I lost track of.
No, it's okay. It's okay. It's okay. This is the last question. You could relax after that. And no, but my question is very simple. I mean, so you have been using ensembles, okay? Yes. And there are also other possibilities. I mean, you mentioned Bayesian methods, Gaussian processes. There are no other types. For example, people are using something called neural processes in order to model uncertainty at the output of the model. And did you had in mind to try something like this? I mean, to explicitly model uncertainty without using multiple runs of your methods?
I think that we could account for other sources of uncertainty. So here I've done the input with my input distribution. Maybe we could consider also in terms of input ensemble of weather predictions, see what are and propagate these ensembles as well. Maybe for the approximation error of the network, maybe I could, based on my study on approximation error, maybe I could add a noise term that accounts for this approximation error. There may be other possibilities, but
okay, but you okay?
Yeah, at the moment, sorry.
Okay, that's fine. So it's okay for me. It's okay for me for the questions. I mean, so do you still questions? I mean, is there anybody in the jury that has still have something to ask to Anthony? Sorry. To Frédéric. Yeah. I just see Anthony written on the screen. Okay.
I have a question.
Yes.
What's your plan for the future?
I'm not sure at the moment. I'm still looking. But I think I'm going to focus more on other applications than wildland fire. And I'm not planning on continuing in academic research, although I would like to continue in research, but most likely in not in the public research. But that's not sure. Nothing is set at the moment. So maybe at some point I will come back to wildland fires and the academic research. I do not know at the moment.
Okay, cool.
Okay. Is that it?
Yeah.
Okay, so we shall stop the question. And so how do we do? Frédéric, you leave the...
I'm going to leave the Zoom video conference and
Okay.
leave the room together with the public in the room. We're going
exactly. With
and
the audience in the room, we are going to stay only Jean-Philippe and me, and of course the member of the jury, and we are going to.
And you all have a discussion, but probably for 20 minutes?
yes, we need to tell the people on YouTube.
Yes, there are people watching on YouTube. So,
so we'll be back after, I don't know how long, maybe 15, maybe more minutes. But we're going to stop the broadcast because the discussion between the members of the jury is private, and they'll give their conclusions only after the deliberation. So we'll be back.
okay.
So I need to...
Yeah, so about 15, 20 minutes probably.
20 minutes, yeah.
meeting.
Okay, okay, I'm going to ask him.
Ben, tu peux venir là?
Oui.
Tant qu'à faire.
Pas besoin de me reconnecter.
Non, je ne sais pas si le live a recommencé.
Okay. So the recording is on.
Recording is on.
Okay, that's fine.
Hmm.
Yeah.
So we shall start. Okay. Okay. So Frédéric, this is the big moment for you. So we had this deliberation at the jury, and so everybody agrees that you did well. Okay, we appreciated your presentation. We also appreciated the answers to the questions, even if it seems that you were a little bit tired by the end. And the jury also made a lot of nice comments about your contributions. Okay, for example, about the diversity of the topics and of the scientific fields that you have been working on or contributed to. And for example, in maths and physics and in computer science also, with a lot of simulation. Okay, also, the jury appreciated that the different contributions, okay, in both scientific and the methodological contributions, the facts that you started with a real world problem, and that you ended up with more or less concrete solutions to these problems, okay. And also the fact that you during your thesis you worked at the crossroad of different disciplines, and we appreciated. All of us know the difficulty to do that, and we appreciated it a lot. Okay. So by the end, we decided that we should deliver you the, I don't know if it's a grade or a diploma of doctor, okay, of Sorbonne University in the mathematical sciences, okay. Well, and we will give you our congratulations.
Congratulations.
Okay.
Thank you. you very much.
On peut pas
So you-
embrasser.
No.
So if you want to say some words before we leave.
Yes, well, first of all, thank you all for taking part in my jury again. I'm sorry, I interrupted you a bit during the defense. I'm really sorry about that. I need to apologize again. And thank you all for your comments and your very interesting questions. I would also like to thank my colleagues from INRIA, especially in the Équipe Ange. Some of them are here present with me today, but also the other colleagues at INRIA and from Corsica and the Firecaster project. And I also need to give special thanks to well, my supervisors. So at first I thought that this would be very complicated. I knew nothing about wildland fires. I felt like that I still had a lot to learn and that there was a lot to do. But I'm very happy with all I was able to accomplish during those 3 or so years. And that's wouldn't have been possible without you, Vivien and Jean-Baptiste. So I learned a lot during this PhD, and you gave me excellent guidance during all this. So thank you very much. And one last thing, and maybe I should stop there. Thank you for all of the people who supported me. I think some of them are following us on YouTube, maybe. So yeah, my colleagues, my friends, and more specifically my mother, my sister, and Louis. But that's it. I think that I may have forgotten people, things to say, but that will be it for now. Thank you again.
Well, thank you.
Yeah.
Okay, thank you and good luck, and thank you to everybody. It was nice to see you. Vivien.
Maybe we should keep this one.
Bye.
Le t-shirt du projet. C'est bon, ok.
Okay, thank you.
Bye.
Thank you.
Okay.
Thank you.
Thank you, bye
Merci Vivien.
bye. Bye.
Merci Frédéric. Au revoir.
Bah, écoute, je suis content de te voir, Vivien. Ouais. Thank you.
Moi aussi. Ouais.
Bah, ça fait plaisir. Voilà. Ça va?